cubic box with sides of length L is rotated about a vertical axis through its center at an angular velocity of omega. The box is completely full of a fluid of density ρ. The box has a closed top except for a small hole in the center at point A. Develop an expression for the net hydrostatic force on one of the four side walls. So the given information is that we have this box. We'll use the diagram that's given. There's a fluid with a density ρ inside the box, and it completely fills the box, but there's a small hole at point A. So the significance of that is we'll know that the pressure at point A has to be atmospheric pressure. This box is spinning around this axis at an angular speed of omega, and we're trying to find the force that the fluid inside the box exerts on one of these four side walls. The box is cubic, and the length of each side is L, as indicated on the diagram. So what we're asked to find here, we'll make a note of that, is the net hydrostatic force on one of the four side walls. Start off with our assumptions list. So the first thing we'll assume is that this has been spinning long enough that the fluid is in hydrostatic state. Next thing we're also going to assume, and we'll see where this comes into the math later on, but I'll put it in the assumptions list right now, is that ρ is constant everywhere and g is constant everywhere. So ρ and g are constant. And we'll see if there's any other assumptions we make as we go along. So we'll begin our analysis. So we've been asked to find a force on a submerged surface. So let's start off by writing down our equation for the force that a fluid exerts on a submerged surface. So now it's a matter of going through and figuring out what all of these things are for this particular problem. So we'll start off with the pressure. Because this fluid is in a hydrostatic state, the pressure field is represented by the basic hydrostatic equation. Now in this case, G, we need to first of all establish a coordinate system before any of these vectors can make sense. So we'll go back up to our diagram and do that. I'm going to let this central axis going up here be Z. So we see that our G is in the negative k hat direction. While I'm at it, I'm going to put the rest of the coordinate system here. So the bottom of the box is going to be the origin. I'll have the x coordinate heading off to the right, and then that means that the y coordinate is heading straight back like this. So that's my x, y, z coordinate system. But for now, z is the only one I need, because I can write down g as minus g k hat. The other thing to remember is this is spinning, so the acceleration is not 0, but the acceleration is going to be equal to minus omega squared r hat. So the r is the distance away from the axis of rotation. So notice I'm already starting to work in both a Cartesian coordinate system here, which I put, but also we'll have a cylindrical coordinate system working because the acceleration can be expressed in that cylindrical coordinate system much more conveniently. So now I've identified both parts of this, so I can bring that into my basic hydrostatic equation, and I'm going to expand the left-hand side as well. So partial P, partial Z in the k hat direction, plus partial P, partial R in the radial direction is equal to minus rho g k hat, so that's the g vector going in, plus rho omega squared r hat. So I've kept the r and k components of the left-hand side because I know I'm going to have r and k components on the right-hand side. So that's my basic hydrostatic equation with each of the components written out on both sides. So what we need here is pressure as a function of r and z. So pressure is a function of two variables because of the spinning. As we move up and down in this fluid, the pressure changes because of G, but as we move radially or towards and away from the axis, the pressure changes because of the rotation. So pressure is a function of two variables. And this tells us the pressure gradient in those two directions. So we can extract the K component from this, and that says that partial P partial Z is equal to minus rho G. So we can integrate that, and it says that P is equal to minus rho G Z. But because P is a function of two variables, this will not just be a simple constant. It is possible for this to be a function of R. So a function of the other variable, because we integrated here with respect to Z. So the constant of integration could be a function of R. That remains to be seen. We can also extract the R component. So partial P partial R is equal to rho omega squared R. So equating that part to this part, and then integrating this tells us that P is rho omega squared R squared over 2 plus possibly a function of Z. So when we look at these both together, we see that the function of R here is that part, and the function of Z is that part. So we can combine these two together and say P is equal to rho omega squared R squared over 2 minus rho G Z plus a constant. Because notice this function could also have a constant in it. So it could have a part that depends on R plus a constant. This could have a part that depends on Z plus a constant. So we have to recognize that that constant still needs to be brought down here. So if we take a look at this expression, what we should just think about, we've come up with P as a function of R and Z. Does it satisfy these two things here that we know that that function needs to satisfy? If we take this expression for P and differentiate it with respect to Z, there's no Z's in here, so this disappears. It just becomes minus rho G, and there's no Z's there, so that disappears. So that condition checks out. This equation for P satisfies that. Likewise, if we take this and we differentiate it with respect to R, then we get rho omega squared 2R, and the 2's cancel, so rho omega squared R. No R's in that or that, so they disappear. So we do indeed get rho omega squared R. So this equation satisfies both of these conditions. So that's a good expression for P. Now we still are left with this constant that we need to find, constant of integration. So again, we're always looking for a known pressure at one location to do that. Well, the place where we know the pressure, as we talked about earlier, is at that position A. We know the pressure there is atmospheric. So we'll let the pressure there be 0, and then we'll get an expression for P, which is a gauge pressure. So our condition is when Z is equal to L, so notice Z equals L at the top of the box because I put the origin at the bottom, and R equals 0 because that point A is right on the axis. So when Z is equal to L and R is equal to 0, the pressure is equal to 0. So that makes it a gauge pressure. So we substitute all of these things into our general expression for P. So 0 goes in there, is equal to, this R is 0, so that whole term is gone. So minus rho G, that Z becomes L, plus the constant. So therefore, the constant is rho GL. So our final expression for P that's ready to go into our force integral will be rho omega squared R squared over 2 plus rho G L minus Z. So that's P as a function of R and Z. So that describes the pressure anywhere in that box. Now the next thing we need to think about is the unit normal and the element of area. So we'll go back up to our diagram. We could pick any one of these four faces to work on. I'm going to work on this face here. Okay? So that face. So the unit normal for that face, remember, It's perpendicular to the surface, projecting into the fluid. So the x-axis points this way, so unit normal to that surface is minus I hat. So I go back here and make a note of that. So the unit normal is minus I hat. And the dA, so again back to the diagram, an element of area on that face, if I were to just draw what a typical little element of area would look like, tiny little square lying on that face. So its dimension in this direction is going to be dy, and its dimension in this direction is going to be dz. So the dA is dy dz. So now I'm ready to bring everything back into my force integral. So that's what I'll do. So the force on the surface, negative the integral of my pressure expression, which is right here. So rho omega squared r squared over 2 plus rho g L minus z. So that's the pressure. The unit normal is minus I hat, and the dA is dy dz. The limits of integration on y are going to be minus L over 2 to L over 2. Limits of integration on z from 0 to L. And that's just because of the way I chose my coordinate system. So we'll go back and look at this. So in the y direction, I have to go from minus L over 2 to plus L over 2. And in the z direction, from 0 to L to cover that entire face. So now we take a look at the integral that we've assembled. And at this stage, we always want to do the same thing. We want to recognize the variables we've chosen to set up our integration are y and z. The only variable that we can have in this expression are y's and z's because of that. So the problem we have right now is this r. This z is fine because that's one of our variables of integration. But this r is a variable. As we move around on that face, it changes. So we need to figure out what is r as a function of y and or z. So in order to do that, I'm going to start a new sketch here. Just go back here. So I'm going to look straight down in the negative z direction. So I'm going to look at the xy plane. Okay. So looking straight down on this thing, I'll see a square. My coordinate system, I'll just put on there, is like this. So that's x and that's y. So I'm looking straight down. Now notice that this face is the one that I'm integrating over. So the surface that I'm integrating over is this face, in and out of the screen. So any point on that face, and I'll just pick an arbitrary point, we can represent the distance. So that distance is the r in this equation, right? The distance away from the axis. So the distance r is that there. So this distance is y, because it's just the y coordinate of that point. And this distance, the horizontal distance, is always L over 2. So as we move this dot back and forth on this surface, the r changes, the y changes, but this is always L over 2. So we always have a right triangle here that we can talk about. And so r squared is equal to L over 2 squared plus y squared. So that's just a right angle triangle. So r squared is equal to y squared plus L over 2 squared. So this gives us r squared as a function of y squared. So notice it's r squared we need in there, so we don't have to take square root or anything. We can just take this quantity and put it in there, and now everything in here is a function of y and z. So that's what we'll do. We'll rewrite that, and it'll be ready to integrate because everything inside of it will be a function of y or z. So while I'm doing that, I'll take out some constants here. This negative sign and that negative sign cancel each other, and the I hat can come out. And also there's a density in both of these terms. So out front, I'll just have rho I hat, still integrating from 0 to L in the z direction, from minus L over 2 to L over 2 in the y direction, And then what we have left here is omega squared over 2 times r squared. So this is r L over 2 squared plus y squared. So that whole thing is the r squared. And then plus g times L minus z dy dz. So now everything in here is a function of y or z. So we're ready to do that integration. So we'll do that next. So we'll do the integration with respect to y first of all. So holding the z constant, integrating with respect to y. So this will be rho I, still have our z integration undone. The y integration we're going to do. So this will be omega squared over 2 y plus y cubed over 3 plus g L minus z times y. And the limits of integration, minus L over 2 to L over 2, and we still have our z integration yet to do. So now we just substitute in the limits. And now we're ready to integrate with respect to z. So that's the final expression for the force on that particular face. So notice the direction is in the I-hat direction, and if you go back and look at the diagram, it makes sense that that's the direction. And also remember, this is the net hydrostatic force because we used a gauge pressure, so it subtracted off the effect of the atmosphere pushing on the outside. So that's the final expression for the force on that particular face. So notice the direction is in the I-hat direction, and if you go back and look at the diagram, it makes sense that that's the direction. And also remember, this is the net hydrostatic force because we used a gauge pressure, so it subtracted off the effect of the atmosphere pushing on the outside. So the last thing to do is just make a statement here that the force on any of the faces has a magnitude shown by this.